for some of the upcoming due dates. We will be finishing lines and linear functions today, and that will be due tomorrow. So if you've not gotten started on that already, please do so. I think if anything, the majority of this material should be fairly straightforward as it pertains to lines. So in particular, linear ideas of linear functions and equations, which should be, I suppose, familiar to those of you who may have had something similar in high school. And then we'll be going through this section 3.4. You might notice that there's two sections due, both of them due on the 5th. This section on 3.4 is incredibly easy, and I'll explain why. And then 3.5 will be a little bit more engaged. So let's go ahead and finish 4.1 for now. And get started. So when we left off, we talked about example 5. So we were in the middle of describing parallel and perpendicular lines and how to find them algebraically. And this is because our visual understanding of parallel and perpendicular is pretty straightforward. Two lines are parallel if they go on straight forever in both directions and they never cross. Perpendicular, we didn't really talk about that one that much. But if anything, I believe the visual interpretation for that one is pretty straightforward. They intersect and form a 90-degree angle. That's one way you can think about it. So algebraically, though, how do we figure this out? How does this translate? We're talking about lines with slopes and intercepts. So how do we translate that visual idea to something algebraic? And I wrote the rule up here. Two lines are perpendicular if one slope is the negative reciprocal of the other slope. So you take one slope, you just flip it. So if one slope was, here, I'll write it out. I'll write out just some quick example. If one line had a slope of 2, and you wanted to find the slope of a perpendicular line, you would flip 2 as, 1/2. It's a flip, just reciprocal flip. And then you change the sign. If it was positive, you would make it negative. If it were negative, you would make it positive. And that's what you do for the slope. That's how you find the slope of the perpendicular line. A line perpendicular to some other line you already have. So let's go ahead and look at a problem. Now, if you printed out my notes, or if you've referenced my notes recently, example 6 will look much different. I changed example 6 right before class. So example 6, I did, in fact, change example 6. So that. Example 6 is different because I give a new line and a new point. So whatever I had before, you could just toss that. This one's going to be more helpful. So they give us a line, x is equal to -16. And they want us to find a line perpendicular to that. Well, if anything, they give us x is equal to -16. So what does that mean? So let's think about that visually. So x is equal to -16. It's not even in y is equal to mx plus b form, because there's no y. There's no y at all. So there's just an x. And if you remember from the last class period, we talked about what happens when you have just an x. It means you don't have a slope, which means we have a vertical line. So this will be a vertical line. because this is not a typical mx plus b form. There's no m, there's no slope, which means that this is a vertical line. But of course, it's not just any vertical line that I can draw anywhere. It has to happen at x is equal to -16. So -16, 1, 2, 3, and I just keep going all the way to the left, -16 times. I'm not going to draw out 16 tick markers, but I think you get the point. And since it's a vertical line, well, what does a vertical line look like? It just goes up and down. So if anything, that's the original line that they gave us. We haven't even touched perpendicular at all. That's just the original line. And now they tell us that we want to find a line, the equation of a line perpendicular to this, and it contains the point -7, -1. Well, what's perpendicular to a vertical line? Well, shock, a horizontal line. I think that should make sense so far. So perpendicular to a vertical line, horizontal line. So if anything, we have the general framework down. It's a horizontal line somewhere. But we don't just draw, because we can draw a horizontal line in a whole bunch of different places on this graph. That's why they gave us the point. By them giving us the point, now we know that the horizontal line has to pass through that point. And if we sort of guesstimate where that point would be, it's to the left 7 and down 1. So it'd probably be somewhere, probably right there. Again, it's not perfect, it's not built to scale, but it tells us exactly where the perpendicular line would go. I will use the color green. So that tells us exactly where the horizontal line would go. And then the final question is, what is the equation of this green line here now? So it's a horizontal line, which we already know what the slope of any horizontal line is. It's just 0. The slope of a horizontal line is 0. So if we were thinking about mx plus b, well, we know that the slope is 0. And then the y-intercept is the last thing we have to figure out. Or additionally, what's the x value? Or a y value, rather. It's -1. Comes from right there. So the final answer would be y is equal to -1. So that would be the equation for the line that is perpendicular to this vertical line that they gave us. So again, if you downloaded these notes or printed them out, example 6 here will look different. So there's a reason why it looks different. I changed it right before class. This one's going to help you out more in the homework. Does anyone have any questions about this before we move on? Okay. All right, so finally we'll talk about, well, at least for this collection of problems, we'll talk about this one problem that's in the homework that compares Fahrenheit and Celsius. And So you're probably all familiar, at least with the idea of Fahrenheit and Celsius. Here in the States, we use Fahrenheit. Pretty sure the majority of other countries, or a lot of other countries, use Celsius. And then the question is, well, what's the relation between the two? It turns out the relation between Fahrenheit and Celsius is linear, which means we can actually determine a formula for a conversion formula between Celsius and Fahrenheit. And we can do that given all of this information. And so what they give us here, they actually give us a rather large plethora of information. So they're telling us that 32 degrees Fahrenheit corresponds to 0 degrees Celsius. And additionally, 212 degrees Fahrenheit corresponds to 100 degrees Celsius. So that should be 100 degrees Celsius. And I claim that we can use that information alone to build a formula that compares Celsius and Fahrenheit. And the reason why I claim this is because what this does is this gives us two ordered pairs. Because the idea of comparing things as a linear function implies that one of these values is an input and one of these values is an output, an x and a y. So in essence, what they do is they give us two ordered pairs. And from there, we can find the linear function, connecting them. And to do that, well, what's the equation of a linear function? It's y is equal to mx plus b. So it sounds like we need an m, which is the slope, and we need a b, which is the y-intercept. So, and we also have a form that we could use, the slope-intercept, or the point-slope form, but that requires us to have the slope. In any case, we need the slope. We need the slope. The slope is very important. We can't do much without it. So, luckily, we know how to find the slope. y2 minus y1 over x2 minus x1, or x1, sorry. x1, there we go. And so we can place in the values for y2, which would be 100, minus y1, which is 0, over x2, which is 212, minus x1, which is 32. And we use this because we do not have a visual representation of the line. There's no rise over run to look at. We don't have a graph to just simply count. And if we did, we'd be counting for a long time, considering the magnitude of these numbers. So 100 minus 0, of course, is just 100. 212 minus 32, it's going to be 180. And so this comes out to be, what is that, 10 over 18, that's 5 over 9. Because they want you to keep everything as fractions, generally. So that's the slope. Now that we have the slope, we can go ahead and use, well, we know slope-intercept, which requires us to know the y-intercept. And we also have the point slope, which requires us to have a point in the slope. I think one formula makes more sense to use over the other. So one of the formulas, we actually already have everything to use. We want to use point slope because we have a point. In fact, we have 2 points, and we have a slope. So let's go ahead and try to squeeze that here. We're going to use the point slope form, which is y minus y1, and y1 is 0. I mean, really, you could pick either point, but we did choose y1 to be 0, is equal to m x minus x1. I'm going to replace x and y. We were using x and y as a replacement for F and C because Fahrenheit and Celsius were acting as x and y respectively. So now I can just replace those with, well, C and F, or F and C respectively. And that would be the answer. The next part asks you to just plug in 60 for F and solve for C. Due to time restraints, I'm just going to hope that you can all figure out that part. Just plug in 60 for F. 60 minus 32 is that 28. Multiply that to 5/9, you get an answer. So if anything, I'll do that part. Does anyone have any questions? And this is normally the process you use if you're trying to find the linear function or linear expression for 2 points. Find the slope, and then you use point slope form, as I did here. Yes?
How do you determine which, like, either Fahrenheit or Celsius you're going to put with X or Y?
Generally, it's an arbitrary choice. I mean, either one could be X or Y. It really doesn't matter. But in this problem, in your homework, they set up the problem weird to make you think that one is X and one is Y, but the answers for this are multiple choice. I don't know if you've seen this question in the homework already, but yeah, the answers are multiple choice, and then they switch them, which means you would have to do a lot more complicated algebra. So in my notes, I just switched them again, or I switched them to what I thought was easier, and it'll help out in the homework more so. But really, you could have switched Fahrenheit and Celsius, gotten an answer with F isolated, but then your answer choices would have had C isolated. So you would have thought, did I do something wrong? Well, no, it's because they kind of tricked you.
So what you're trying to find is Y.
What's that?
So what you're trying to find is Y.
Well, you're trying to isolate a specific temperature, and the multiple choices all have C or Celsius as the isolated temperature. In the problem, you would look at everything swapped, so you would be tempted to put F as your isolated value, but then your answer choices would have C. And I've had students before say, what did I do wrong? And you didn't do anything wrong, it just, there's more work from here. This simplifies that process. In general, it's an arbitrary choice. This is just a math lab nitpick, which shouldn't be too surprising that math lab is nitpicky. Any other questions? So yeah, if you printed out the notes, you might see that everything was swapped around. I swear that was the only 2 changes I made to the previous problem, and then I swapped some of the numbers. They're the same numbers, I just swapped their order. So if you do have my notes printed out, the numbers it's the same numbers, their order is just swapped. Okay, well, let me go ahead and start talking about linear functions, which isn't too much of an extension from linear equations. It's just instead of using y is equal to mx plus b, sometimes we'll call it f of x is equal to mx plus b. Generally, we like extending expressions and graphs to functions. So it's the same exact mx plus b form. Instead of y, though, it's f of x, which is just a notation change. In your homework, it'll reference something called an average rate of change. The average rate of change, but since we deal with linear functions, that's the same thing as the slope. So if they say average rate of change, it's the slope. So they'll ask you for some random linear function and ask what the average rate of change is. Just give them the slope. That's it. And the next bullet point says a linear function is increasing if the slope is positive, decreasing if the slope is negative. I think that makes sense. Positive slope means increasing. So that's what the next point says. So all of that should help with a few homework questions on its own. Just those little bullet points. And to set up a linear function, so in example 8, a car rental company charges $210 to rent a car and 15 cents per mile driven. And all they want is for you to write a linear model using not necessarily a y value, but they're actually saying a c, the letter c, just for cost, and driving it X miles. So we are just simply setting up a linear function. It's really a one-line thing. So if anything, no matter what, they're going to charge $210. And they're going to add that to, well, they're going to take 15 cents out of every mile you drive. So how would you represent that expression? 15 cents per every mile, or for every mile. It'd be a multiplication. 15 cents for every mile. And then they wanted us, so notice that is mx plus b. So it also helps that they told us that they wanted a linear model, which is a fancy way of saying what's the mx plus b form of all of this information. And they wanted us to call it c of x. Again, that's what distinguishes this from the previous stuff. It's fancy notation. I think this problem is multiple choice, if I remember correctly. May not be, but it's a one-line thing. There's also a few problems, like example 9 here, where they give you a table of values of x and y values, and they want to know if this trend is linear or not. And I say trend instead of a line because that table of values on its own is technically not a line. It's just a collection of points. They give you ordered pairs, and so that's ultimately just points. They want to know if you were to connect all those dots for all those points, would you get a line or not? Or would you get something else? So we can actually figure this one out fairly quickly. Because what you're doing is between the y values, you want to know what the trend looks like. That's normally what a slope does. It finds the trend between y values, also known as an average rate of change. So the difference between -3 and -8 seems to be -5. The difference between -8 and -13 seems to be -5. That's an interesting pattern. Negative 13 and negative 18. Negative 5. And then negative 18 and negative 23. Negative 5. Okay, well, is that a coincidence that we got the same value? I mean, in essence, what this means, it is a linear trend. And you'll never guess what the slope is. Maybe you will. What is the slope? It's negative 5, yeah. So that trend between the y values, that's the slope. So there's maybe 2 or 3 problems like this, and that's pretty much the process. If that displacement is not the same, so let's say we got negative 5 and then negative 6 and then something else and something else, well, that's not going to be linear. I mean, your trend between values has to be constant. Has to be constant. When I ask you for the slope of a line, you don't tell me 3 different numbers. You tell me one concrete number, because the slope is a constant thing. It's a static thing. So it's linear if all the numbers are the same. Hopefully that should be pretty straightforward. I was told I was going to get a new computer in here today. I did not get a new computer in here today. Maybe I'll get it next week. Hopefully. Okay, there's, to conclude this, let's see, there's this one and this one. Okay, cool. So to conclude this section for the homework that will be due tomorrow, they also have some of these problems. I'll go ahead and talk to these right quick. Okay, so they'll give some graphs and you have to determine some information about it. It's merely identification. So they give us this line, this linear function here. They give us some points in the line, and then they go ahead and ask us some questions about it. So part A here, it wants us to solve f of x is equal to 0. There's nothing really to solve. I mean, we don't really have a function. So f of x is equal to 0. That just means y is equal to 0. If I look at this whole graph, where's y equal to 0? Down here for that point, because there's a 0 in the y spot. So then what's the x value corresponding to that? It's just negative 8. That's part A right there. When we solve a function, we find the x values. So part B may be a little bit more engaged, because part B wants us to figure out when the function is greater than 8. All right, that's kind of an interesting way to ask it. So when is the function equal to 8? Seems to be right there. And so when is this line greater than 8? Obviously, when it goes up. So this right here. So to solve it, we need to characterize it using x values. What we just did was we highlighted an interval, which means, well, this problem is going to ask for interval notation, no doubt. And so with this interval, remember, with intervals, you find the smallest point, the smallest x value, that is, from the leftmost point, which is 8. And from the right-hand side, we get infinity, because it just goes on forever. This would be eight to infinity. Or x is greater than 8. I really can't remember which one they ask. Interval notation or inequalities. They go back and forth all the time, so I'll just give you both of them. All right, so part C. Part C wants us to determine when the function is less than or equal to 15. When is the function equal to 15? Right there in red. Now we need to see when the function's less than that, which means we go below. Just like that. And so we play the same game of determining that interval in some way. We always start with the leftmost part of the interval first. The leftmost part seems to be negative infinity. The rightmost part seems to be 22. Because again, we regard intervals based off of x values. I'm going to use a bracket here for 22 because the problem has an equal to component, as opposed to the previous problem, which did not. So I did not use a bracket. And again, I can't remember if they want interval notation or an inequality, so I'll put both. So then finally, part D wants us to determine when is the function trapped between 0 and 15. So when is the function 0? Seems to be right here, which I'm coloring in black. And when is the function 15? I'll color that in black as well. And so we look for that region connecting the two. The lowest or the leftmost x value is -8. The rightmost x value is 22. And so we can characterize it as -8 to 22, where we use parentheses for both of them because there's no equal to part. So it's really more so just identification, but this would be the process for doing so. These problems are a little tricky, and it might be that you have to do this problem once in MyMathLab. You get it wrong, but when it tells you the answer, you see why that answer applies to the graph you're given. And then see, okay, I've used the y values instead of the x. So it might take you 2 or 3 tries, but you should be able to knock it out fairly quickly otherwise. Does anyone have any questions about this one? Okay. one more problem, and then we are done with this section. It's another, they give us, well, here they give us not one line, but 3 lines. They're all in blue here. And we need to answer parts A and B. So probably the hardest part of this problem, well, definitely part B, which really isn't that bad once you really dissect the mess that is going on here, because there's just a lot going on here. So part A, of course, asking for solving the equation when f of x is equal to g of x. When you solve an equation, you generally are looking for x. So it wants to know the x value such that when the line that corresponds to f is equal to the line that corresponds to g. And what does it mean for 2 lines to equal? Really all that means is, yeah, they intersect. All right, so which one of these lines is f? Seems to be that diagonal line. One of the lines is G. Seems to be that lower horizontal line. Where do those 2 lines intersect? Seems to be right here where those 2 lines intersect. And solving means get the x value. Done. So that's all you have to do for part A. Part B tends to be the trickier one, but that's because of the mess that's going on. By dissecting it, it may seem a little bit more clear. So for part B, it wants to know when f of x is in between g of x and h of x. All right, so f of x is in between g of x and h of x. Well, f of x is the diagonal, g is the lower one, and h is the higher one. So it wants to know when that diagonal line, is trapped in between 2 horizontal lines. Let's see if we can shade that region. So it wants to know when the diagonal line is greater than this horizontal line and lower than that horizontal line. That's what it's looking for, that shaded part I just shaded in the color black. Because that is when f of x, the diagonal line, is greater than the lower horizontal and less than the higher horizontal. But once you identify that, well, now we have an interval, which means to determine the, well, either inequality or interval notation. Here I actually put interval notation, so we'll just worry about that. We need to figure out the leftmost side of this and the rightmost side of this. And we use the x values for this. So -8 from the leftmost side, 4 from the rightmost side. So we got a -8 and a 4. And then we determine if we use brackets or parentheses. Well, we use bracket for -8 because there was an equal to part on the inequality for that value. And we use a parenthesis for the 4 because there is a less than sign for that one. That would be part B. These problems are a little tricky to break down, but the statement, there's no computation to it, it's just identification. Again, it might be something where you might have to do it the first time, it says you're wrong, you look at the numbers and say, oh shoot, I mixed something up. And then you try it second or third time and you get it. Does anyone have any questions?
If it would ask you to write it in form of an inequality, would it be written in a compound inequality like that, where you would?
Yes, let me go ahead and do that. So if you were to write this as an inequality, it would have to be as a compound inequality. It would be just like that, because generally we use compound inequalities when there's no infinities present. So that would be the compound inequality if you had to write it, which doesn't seem like you have to for this problem, but there you go. So if that's it, and of course Google Meets. Okay, so other than that, that is everything you need in relation to trying to figure out how all this moved on the, all right, anyway, this is everything pertaining to linear functions. And so that homework is due tomorrow. So if you have not started on linear functions already, please go ahead and work on that and get that done. But other than that, let's let me just start that over. We're going to go ahead and pick up on the next section after I reset the writing stuff. Okay, so we're going to move on. So library of functions and circles. All right, so one of the hurricane stipulations is now circles is just gone. You might have noticed in your homework, or you might not have. All the circle problems should be gone. Or if they are there, you should already have gotten credit for them. It's one of the two. But we're not talking about circles, which means this section only pertains to library of functions. And a library of functions, it's also called parent functions. You might have heard it with that terminology. And it's a way of knowing the shape of a function based off of its most dominant term. When I say dominant term, so we know all, for example, all linear functions take on a shape like this. It's just some slanted line in some direction, but its most basic form is this identity function, as it's called. Quadratics tend to take on this cup shape or parabolic form. We'll talk more about squares and quadratics later on, but they may shift and transform a little bit and all of these things, but at the end of the day, that shape still relatively looks the same. So these parent functions give us an idea of the structure of the general structure of these functions and how they behave. Cube looks like a snake, square roots looks like, these are parent functions we'll slowly talk about throughout this semester. And for the homework, there's nothing for me to really write down for this section. It's just you're given 8 graphs, and in the homework, you're going to be asked to identify these graphs, and you have the notes right in front of you. It will give you a shape that looks like this, and it'll say, which function is this? And you click on identity function, and it says great or fantastic or whatever. So this section's pretty straightforward. There's nothing to really talk about. So it's just, if you can match shapes to words, then you'll knock that homework out in like 5 minutes, I promise. And like I said, circle stuff, just not even talking about it. Not talking about circles. That's just removed from the class.
So it's not going to be covered on either of the tests?
No. No circles. No circles anywhere. So all this is just gone. We skip all of it. And we get to graphing with transformations, which definitely will be on tests in the future, which will definitely be prevalent for sections, well, pertaining to, of course, this one, but other sections in the future. Transformations come up quite a bit, and they are directly related to the library of functions that we talked about in the previous section. So if we know the general shape, so let's just say that cup shape, if we know the general shape, then what about if we want to transform it in some way? Say if we need to shift it in some direction a little bit, or if we need to stretch it out or bring it in. Well, this section is going to talk about how these shifts, apply algebraically. Again, it's another idea, thinking about how graphs are associated with functions. And we're going to start off with how you would shift a function. And of course, there's two types of shifts. You could go left or right, or you can go up and down. That's the sort of shifting that we can do, of course, relative to the cardinal directions. But so visually that makes sense. You think of left and right, you have spatial awareness, so you know left and right, you know up and down, but how does that apply algebraically? And how that applies algebraically, the vertical shift, which is up and down, is when you add a number to the outside of a function. We'll talk about what that means outside and then ultimately inside. So if you want to shift a number up by 2, you add 2 to the function. If you want to shift a function down by 3, you would subtract the function by 3. And I also say the shift is verbatim, which you might wonder what that means. It makes more sense when I talk about a horizontal shift, which notice it says the word opposite at the bottom. So I talked about up and down. What about left and right? Well, this is when you add a number not to the function. You have to add the number directly to the x variable. So wherever the x variable is, you have to add the number such that it is being added to the x directly. Again, I'll talk about this in these next upcoming problems. So whatever that shift is, so if you want to go, to the right 2, notice I say the word opposite. If you want to go to the right 2, you have to subtract x by 2. It's the opposite for left and right. It's kind of an odd stipulation. If you want to go to the left 4, you would have to add 4, which is weird because left is a negative direction, but now you're adding 4. But we will see that momentarily, and these nuances become more clear with repetition. Let's look at example 1 and kind of put these to the test. So it says apply the appropriate transformation, and you won't have to sketch this with any difficulty, as MyMathLab, although it does have this graph up, it has various options you can pick to where it virtually plots the graph for you. All you have to do is tell it how much you shift in a various direction. And for some problems, it'll give you that little box I have on the left side of the screen, which we'll talk about when we get there. So example 1, we are going to apply the appropriate transformation to the function provided below. So for problem 1, y is equal to the square root of x, and this is shifted to the left 8 units. Well, the first thing we want to do is, we want to figure out how that looks on the graph. And To know what its shape looks like, we're going to go back to that library of functions. So remember, square root of x. Okay, square root of x. Let's keep that in our minds. Square root of x. Fact. So for number 5 here, the square root function, it's this arc. So that we know what the shape is now. We have an idea of what the shape is. And so what it says is take that shape and move it, I think it said to the left 8. So we're going to take that exact shape, just move it to the left 8. So that shape did start at the origin. We shift it to the left 8, so that's -8. And the shape had this arc style to it. Again, MyMathLab will do this for you, but it's going to look something similar to this. And so now that we have the graph, let's try and build what this function will look like. So we had the square root of x. And what does it mean to, so now we're going to look at this algebraically. What would be the function that would correspond to this? So going left or right, the rule was we have to add or subtract directly to the x variable. That was the rule for going left or right. And since we're going to the left 8, we have to do the opposite operation, which means we have to add 8 to the x variable directly. What that conforms to is square root of x plus 8. Notice the 8 is in the square root because it has to be right next to the x. That's what it means to shift left or right. You have to add or subtract to the x variable directly. So that would be the function. The problem moves on to ask for the domain and the range as well. And we have the graph, so we can figure out that pretty quickly. The domain is left to right, and it deals with x values. The furthest to the left seems to be, trying to characterize it in the color black here, it seems to be -8. And we use a bracket because that point is part of the graph. And the furthest to the right, we get that arrow. So that would imply infinity, which always gets a parenthesis. And then the range, it's bottom to top, and it's y values. What's the lowest point on the graph? Well, I already have it highlighted. That's the lowest point on the graph. What's its y value? 0, which is part of the graph. So we put a bracket. What's the highest point of the graph? I have that highlighted as well. It's actually infinity. There's no barrier here. That'll make more sense when MyMathLab graphs it for you. Before you have any questions, let's look at problem 2 and then see if that kind of connects anything for you, and then I'll ask if you have any questions. So problem 2, it's a different function, and now they say go down 5 units and simultaneously go to the right 3 units. So the first thing we do is we need to know what the shape looks like, x to the third. So if we scroll up right fast, x to the third is on the right there. It's called the cubic function. And normally students like to call it a snake type of shape. That's perfectly fine. It's got this snake-like curvature to it. So that is a perfectly sufficient representation. And we need to take that shape, or that snake shape, and we need to shift it down 5 units and to the right 3 units. So shift it down 5 units, 1, 2, 3, 4, 5, and to the right 3, 1, 2, 3. And so that's where the snake shape will sort of start to turn at, because it kind of levels out and then goes right back up. So in other words, this would be the snake shape. Again, my graph isn't too great, but my math lab will make an easier illustration for you. And so now the question is, how do we represent this as a function like we did before? How do we rewrite x to the third? Well, to shift down 5 units, so going up and down, that means we have to add or subtract to the function directly. So if anything, that one's normally easier. So that's to go down 5 units alone. So that one is down 5. But we're not done, because of course we have to go to the right 3. And that means going left or right means we have to add to the x directly, not indirectly like the 5 is doing. And it has to be the opposite. So to go to the right 3, we would have to subtract x, or subtract 3 from x. So finally what we have so notice it's right next to the x. So that means whatever the function is, we need to find a way to incorporate that left or right shift into the function itself. We can use the graph to determine the domain. Luckily, because in every direction I see arrows, we're going to get infinities all throughout. There's no just abrupt stops. I know my illustration doesn't do it justice, but there's no sharp arcs that imply any sort of barriers. So these are both negative infinity to positive infinity.
So technically, it would be safe to assume that regardless of transformations, domain and range is always going to be infinity when it comes to the cubed.
Yeah, cubic functions always have unlimited domain and range.
Regardless
Just
of
always,
transformations.
yeah.
From parent function to new function, the transformations, we're still looking at infinity to infinity for it.
Yeah, cube functions always, that's always the case. Every time.
Thank you.
Yep. So does anyone have any questions about this? If not, I mean, this whole section, we're going to be doing stuff just like this. So if you do have questions, you might, your answer might be, I don't know what I'm trying to say. I need more coffee. And everything shifted on me again. Let's do this again. No. All right. 1 second, everybody. Let's do that. View, transparent. Cool. All right. So like I said, we're going to be doing stuff like that and slowly throwing things in as we go as well. So for example, we talked about moving a graph, how to move a graph left to right, up or down. What about if we want to compress it or stretch it? So what about if we have, say, a cup shape and we want to compress it or stretch it? What do we do? How does that translate algebraically? Well, generally, a compression, so really the way the problem works itself out, you don't have to know the difference between compression and stretch. It doesn't ever put you in that position. I want to foreshadow a little bit. Notice this black box down here, and you should probably get familiar with it because you will see it quite a bit. It will construct the graph for you when you type in a few numbers that you found. Notice it says vertical stretch or compress or compression, which means you don't have to know which one's which. It kind of does it for you. But the principle of what is a vertical stretch or compression, you just multiply the number to the function. You just multiply the number to the function, or it is the number multiplied to the function. So shifting left, right, up, or down, that was all additive. You add or subtract stuff. Stretching and compression, that's multiplication. So that's how you could slowly distinguish these in your mind. Generally, y is, because we deal with functions, y is normally just isolated at all times. But this is, I don't want to say, let's look at example 2, and maybe that'll explain things, because it's not technically to the y. So in example 2, so obviously the 3 here is multiplying x minus 3 squared. But that 3 is not multiplying the 1 back here. 3 is still the vertical stretch, or yeah, it's still the vertical stretch, but it's not multiplying the 1. So it's not multiplying the y, but it's multiplying something. And that's all that matters. It's multiplying something that has an x in it. So that one's, normally I kind of hand wave that one. But in fact, I think this might be in reference to how we apply transformations. We generally apply them in a certain order, where the multiplication happens before any shift up or down. So I think that might be the best way to answer your question. But with all of that aside, let's look at example 2, which does incorporate a compression of sorts. So it wants us to do some stuff for the following function. So here's the function. So here's the function here, and you might be able to notice from looking at the graph what the shifts would be. So looking at this graph, would you be able to determine how much we're going to the left, how much or going to the right, how much we're going up or down, how much are we stretching or compressing? And if so, the way it words things in part A, so notice the way I have it in part A, you fill in the blank with left or right. So how do we determine left or right? What's the characteristic for that? Left or right is the number directly affecting the x. What number is directly affecting the x? Seems to be that -3. That -3 that's subtracting the x directly. So that tells us left or right. But that value is opposite, which means subtracting 3 would mean go to the right by 3 units. Go to the right. And then the next part, okay, so that part does ask for stretched or compressed, but in general, besides for part A, it normally just does it for you. If you're multiplying by a number greater than 1, you get a stretch. If you multiply by a number less than 1 and greater than 0, that's a compression, that's a compression. We're multiplying by 3, which is greater than 1. That means that would be a stretch. So stretch would be for the next one by a factor of 3. And then up or down, well, there's only one number left. We took care of the 3 in the front. We took care of that 3 in the parentheses, and now there's just that 1, which tells us up 1. So up by 1 unit. So that's part A. Part B says use the graphing tool to graph the equation. So the graphing tool, I have it here because I wanted to explain how it works. So it simplifies this whole process big time. The first thing you would have to do to even get to this point is you would have to pick the shape. I mean, just like at like McDonald's or something, when you're messing around with the monitor, it's got the picture of the hamburger and you click on it and it does that. On this, it has the pictures of the shapes. So we'll have the cup shape, the parabola, it'll have the snake shape, and then you click on whichever shape you want this graph to take the form of. So we have to look at this and determine what shape does this take on? And how do you even look at this and determine what general shape it's going to take on? Well, what you have to do is notice one very important characteristic of this, the square, the second power. That second power tells us the parent function. So remember, those are the library of functions that we talked about before. So if we scroll up right fast, what's the square function look like? Over here on the left, number 3, it's the cup shape. So by identifying that, now we know what the general shape looks like. It's going to look like a cup. And it's going to be a cup that's shifted around in some orientation and then, I suppose, stretched out more so by the stretch compression criteria. So if anything, we know that this will take on a cup shape. And once you click on the cup shape tool in MyMathLab, then this box will show up asking, all right, where do you want this cube to go? Where do you want me to place it? So we'll go through that one by one. So the vertical, we'll just go through them, like I said, one by one. stretch or compression. Again, it doesn't ask for either or, it just says, which one is it? I don't care if it's compression or stretch, I'll take it from here. And that's 3. That's the 3 in the very front. So in that little box there, you would just type in 3. And you will notice that the cup shape will, let's see, it'll actually get, pretty sure it gets skinnier. I always get them mixed up. You will see the dynamic change in the cup whenever you change any one of these values. It works real time with how you interact with it. So that would be the vertical stretch. In this class, I've never seen one problem that ever deals with horizontal stretch. So forget it, just keep it at 1. This horizontal stretch thing right here, you just leave it alone forever. I've never seen a problem that's dealt with it. The vertical shift. That's going to be up or down. We said above that this goes up 1. So there's a little slider. You would just slide it to 1, and you will see the graph go up 1. So if you forget which one vertical represents and which one horizontal represents, just move the slider around, and it'll either go up, down, or left, right. The horizontal shift, we said that that was 3. We're going to the right 3. And by doing all of that, we go to the right 3. 1, 2, 3. We go up 1, 1. And then it will generate this cup shape for you. It'll probably look very similar to, probably not that because I drew it horribly. It'll look something like this. It'll be perfect whenever you put in those numbers. So it simplifies this process big time. So we're not done. So from here, let's see. Something like that. Okay. And then it says find the missing coordinates on the of the points that lie here. So this part's kind of tripped up students a little bit. I mean, if anything, the numbers that go into these values over here, it just wants you to plug in the X value and figure out what Y is. So if you plug in -2 minus 3, -5 squared, 25, 75, 76. So that's right. So 0, 9, 27, 28. And then I'm doing it wrong just like I did last semester. I'm sorry. I did that last semester too. Okay, sorry. Yeah, it even says it right above. See, this is why I need coffee. It says plug those points into here. Okay, glad I caught it this time. Last semester they were not very happy. So it says plug these numbers into that function there. So -2 squared is obviously 4. If you plug in 0, 0 squared is 0. 2 squared is 4. Well, I'm out of time, so that's all I got for today. So what I'm going to do, because I ran out of time, how much more do I have to do? So before you all start scattering, tomorrow, instead of the tutors helping you all out, I need to get this done. So if we have extra time afterwards, I'll help you with any homework questions you may have. So I'll help you after class, I don't care. But tomorrow I'm gonna send out a link and it's just gonna be one Google Meet session with all of us, because we don't have class, physical class on Friday. So I'm gonna just lecture from here, so please show up to that. And then if I have extra time or even after time's over, I'll just answer any homework questions you have. So if you have any homework questions, just come bring them to me. Other than that, if you have any questions for me, come up and ask. You're free to go.
I have a question.
Sure.
Where is the tutoring center?
The tutoring center, the Center for Student Excellence, you can find that in Tinsley Hall, which is actually nearby. Let's see, we're in Mead. I'm pretty sure it's that way. It's the building just straight that way. It's on the Friendship Circle part near the very beginning. But yeah, it's a building called Tinsley Hall, and that's where you can find the tutoring center for the Center for Student Excellence. And I believe they have walk-in appointments that you can utilize. That's the only tutor I've heard of that's active so far. They do have good people over there. I've checked it out. I've got a good vibe from it. So yeah, so try to check out Tinsley Hall and try to do that sooner than later because their spots fill up rather quickly. So hopefully that helps you out.
Thank you.
Yep. Oh, is today is Wednesday. Okay. All right. So Molly made a good point for those of you still in the Google Meet session. Yeah, I meant to say Friday. I think I said tomorrow. Yeah, I meant to say Friday.